Hello everyone, welcome to PCIe session today. My name is Chiu. I'm with the PCIe Applications Engineering team at Tektronix. Today I'm going to talk about PCIe Gen5 Receiver calibration. I'll start with what are the things needed to perform the receiver calibration, and then take a deeper dive on how do we perform the calibration. Share some knowledge from the technical specifications point of view, as well as some empirical learnings. Let's start with a list of prerequisites. We want to prepare the following items before we start the receiver calibration. Hardware-wise, we want to prepare a BERT. We recommend Enricho MP1900A, either with a SI or a PEN4 PPG module will work. A Tektronix DPS 70K SX series oscilloscope with higher than 50 gig bandwidth, and then a PCIe Gen5 fixtures. We also wanted to use the latest software and also the automation software, Tektronix test, so that it provides a automated process helping the user to make it easier for completing a calibration. So the software, MP1900 firmware, recommend a version 8.03.13 or higher. Tektronix test software application, that is the automation software, I recommend 6.3.1 or higher. And also SIG test Phoenix is required for performing the DSP analysis. We have a Tektronix performance oscilloscope configuration guide that documents all the parts and pieces needed for the Gen 5 CAM calibration. Once we have prepared the required hardware and software, we can start a receiver calibration. The receiver calibration primarily have two parts. One is called TP3, test point 3. That is the short channel directly connected with the signal source, which is the BERT. And the other is called TP2, that is the end of channel, which is with the ISI channel inserted, and we calibrate that end of channel I. Some of you might have performed receiver calibration for the previous generation, such as PCIe Gen4, might see that TP1 calibration. Since Gen 5, there's a redefinition of the calibration plane to include a cable connected to the signal source. So that now it's called TP3 for the short channel. A couple things worth noted for TP3 calibration. Number one is D-skew. Make sure the scope is being D-skewed, because that's very important that we capture the right skew from the intrinsic instrument. And then we want to launch a Tektronix service before starting the Tektronix test automation software. And then we can see a physical connection shown in the Tektronix test application that indicating what are the connections required for the calibration. The TP3 calibration procedure is pretty straightforward. The automation software, Tektronix test, will perform the following calibration steps sequentially, that is defined in the PCIe 5 test spec, which contains the AC-DC balance, amplitude, TX equalization, which is calibrate the presets, and random jitter, sinusoidal jitter, and also the insertion loss measurement that is going to be used for the removal for the TP2 from the short channel. So after completed TP3 calibration, we'll move to TP2. TP2 are generally more challenging given the knob parameters we will want to sweep across, as well as the tight eye height and eye width range to close the calibration. So we're going to describe what are the steps needed for TP2 calibration, as well as some things that worth keep an eye on, and also some best practice for closing the stressed eye calibration. So a couple things here. We want to make sure a recently completed TP3 is loaded. We want to make sure we select the right device under test type for TP2 calibration. That is either the adding card or systems, because they have the different requirement for the channel budget. And then the Tektronix test automation software will perform the following calibration steps for TP2. The first is DMI, differential mode interference. That's going to be sweep across 5 to 30 millivolt of 2.1 gigahertz sinusoidal wave of 40 nanoseconds. And a CMI, common mode interference, that will be calibrated at 150 millivolt of 120 megahertz sinusoidal wave of a longer 62.5 microseconds. And then you run the optimal presets and CTLE. That is going to search from all presets and the CTLE combination that yields the best eye area. The eye area is the eye height times eye width. And then with that optimal preset and CTLE, we can run a stress eye, which the automation software will adjust SJ, DMI, and ISI, and maybe amplitude to fine-tune the eye height and eye width that is going to be in the specific range that is defined in the spec. So what is usually the most challenging part for TP2 calibration? One thing on top of the list would be the selection of the ISI trace, which is the differential pair on the ISI board. The symptom we see can be that from the Tektronix test automation software, showing that the calibration runs but does not converge. If you see that, you're not alone. We mentioned that there are 4 parameters that we can sweep: SJ, DMI, ISI, and amplitude. SJ, DMI, and amplitude are all going to be swept automatically by the automation software, but the ISI trace will need to be physically connected as part of the operation, and usually we may not be getting the ideal one in the first attempt. The ISI trace connected will be shown on the connection diagram from the automation software for either the adding card or system calibration. The latest 5 test spec recommends we start with the high limit of ISI, that is 37 dB total insertion loss for Gen 5. In that way, we only need to be moving in one direction, just reducing the loss if a solution cannot be found. So in that case, we just want to change the pair in order to close the calibration. And how do I know what ISI trace to use? The test spec recommends using the VNA characterization of text fixture. There's a appendix documented the detailed steps from the appendix B of PCIe Gen5 test spec. And if we don't have a VNA, there's a CSIM-based insertion loss measurement that is a built-in capability in the Tektronix test automation software. And the goal is to land an ISI trace in range that is 34 to 37 total insertion loss, and that can get to a stress recipe yielding the I height and I width in range. So the VNA characterization of text fixtures described in the Appendix B, PCIe Gen5 physical layer test spec. The procedure might take about an hour or an hour and a half, but enables user better overview and precision of the ISI trace to use for the TP2 calibration. If you don't have a VNA, having a third-party lab to characterize your text fixture can also be an option. And here's a snapshot of the steps that is described in this test fixture characterization. So we'll be looking at the selection of the variable ISI parts, and it describes the inclusion of coaxial cables and adapters, and the insertion loss per inch on the ISI board, and the coaxial connector, which is the MMPX for Gen5 loss, and then measure the compliance space bore and compliance load bore loss and the connector loss. Then determine the loss split for CVB and CLB, and then finding the correct variable ISI pairs. And then it describes the target loss values for system RX calibration, adding car RX calibration, and TX signal quality. We'll take a deeper look on the target loss values and the diagram that describe how we split the channel loss for the receiver calibration. Here's the system RX cal full channel loss look like. Note that for Gen5 we have a total loss of 34 to 37 dB loss. So that for the system receiver cal, we have split for the CLB side, that is going to be 7.5 to 10.5 dB variable. On the CBB side, that's going to be 26.5 dB fixed. So let's take a look at how that each side breaks down. On the CLB side, as mentioned, we have 7.5 to 10.5 dB variable. So that's going to be 3.5 to 6.5 dB on the variable ISI board, including cable, with the 4 dB CLB RX trace that is going to be fixed on the CLB. On the CBB side, we have 26.5 dB fixed, with a 8.5 dB package loss that is going to be embedded through the S4P or filter file. So a physical ISI of 18 dB is something we want to look at. That is going to consist of a cable of nominal 1.5 dB variable ISI board for 12 dB trace, and then 3 dB CBB TX trace, and a 1.5 dB for the CAM connector. So this is an overview of the total loss. So we want to know that when we choose the variable ISI on the ISI board, we want to move on the trace from the CLB side, where we have a 3 dB range that can be selected. On the adding card receiver cal side, here's the diagram for the 4 channel. So we'll look at the adding card side. The bird, the signal source, is now connected to the variable ISI, and then to the CBB, and then to the CLB, and with a short trace to the real-time scope. So that the channel loss split would be on the CBB side, we have 24.5 to 27.5 dB variable. That is for 20 to 23 dB trace on the ISI board, including cable, plus the 3 dB CBB RX trace and the 1.5 dB CAM connector. On the CLB side, we will want to fix 9.5 dB loss, including package, which is 4.2 dB. So the cabling and the variable ISI trace will need to be at the 5.3 dB fixed. So the figure shows the reasoning of selecting the corresponding trace number on the variable ISI, and by characterizing the ISI board, giving us more confidence how to make the selection of the variable ISI trace. Now that we have a better overview of what are the channels of variable ISI represents for the receiver calibration, let's talk about some pro tips, so key takeaways we learned for closing a stress eye cal. So first is that we want to perform the DMI and CMI calibration with a nominal channel loss at TP2. That is going to be 36 dB minus the package loss to be used. And that is dependent on if you're calibrating for adding card or a system. And after completing DMI and CMI, adjust the ISI channel pair by adding 1 dB so that the total channel loss is 37 dB, including the package loss, before moving on for optimal preset and CTLE and stress eye. That is the recommendation from the fire test spec. Always want to start with the higher limit, which is 37 dB total loss for the optimal preset and CTLE. So that idea is number one, to comply with the tiebreaker rule defined in the test spec, that always the highest ISI channel should be used if a solution of stressors, HADMI, ISI can be found. And number two, only adjust ISI channel in one direction, reducing the channel loss if solution cannot be found. And anytime adjusting the ISI channel, optimal preset and CTLE must be rerun before running the stress eye, because we want to make sure the optimal preset and CTLE is found correspond to that specific ISI channel. Moving on, after the optimal preset and CTLE step, we want to look for the eye width and eye height ratio of 0.6 to 0.7 range. This is one of the key that we learned from empirical, that stress-I recipe can be converged after a certain amount of experiments. And the ISI typically has more impact on eye height rather than eye width. Therefore, if the eye width and eye height ratio is less than 0.6, indicating there's room for reduced eye height, you want to increase the ISI trace. On the other hand, if eye width and eye height ratio is larger than 0.7, we might want to reduce the ISI trace. And for stress recipe, it actually allows the manual entry of SJ-DMI. That is a valid approach. And the automation software Tektronix test also supports user input of these stressors. And typically, the SJ has more impact on eye width than eye height, and DMI has more impact on eye height than eye width. And amplitude is typically the last parameter that we adjust. We almost never seen the need for adjusting amplitude for closing the calibration. With that, I hope you will be more comfortable running the receiver calibration for PCIe, and will have more clue where to go in the case that calibration does not close in the first attempt. So here we put some more resources that you can refer to for more information. It's going to be in the PCI SIG members area under compliance program and PCIe 5.0. You can find the PCIe 5.0 physical layer test specification, and also the Tektronix PCIe 5.0 link equalization MOI, that is also going to contain the receiver calibration procedures and some of the tips in the MOI. So that concludes today's session. I want to thank you for your time taking the session. Hope you will find the content useful, and feel free to reach out to me if you have any question or feedback. Have a great day, and we'll see you next time.